15.3, so we're coming back to this idea of conservative vector fields, and we'll see, all right, in 15.2 we integrated over vector fields, line integrals over these vector fields, and we'll see that if the vector field happens to be conservative, we have a really easy approach to this. And so let's recall the fundamental theorem of calculus. Oh, I just crossed out what I had. Let me just do it this way. AB, so I'll just say it. All right. If you integrate the derivative from A to B, what do you get? How do you evaluate? How do we integrate anything? We take a function, we find its antiderivative, right? And then we plug the bounds in. So what's the antiderivative of f prime? It's just f, right? And so then you take f and you plug in your bound, right? So b minus f a. That make sense? So the point is that if we have a conservative line integral, we have basically the analogous theorem here. Maybe I'll try to squeeze it in here. So the fundamental theorem of line integrals. Okay, so it's basically the same thing. Let f be differentiable with continuous gradient, and let C be a smooth function, a smooth curve with parameterization so there's kind of the setup, right? I was pretty lazy in my statement of the fundamental theorem, but essentially that's, right, let f be a function that's differentiable. So that's kind of what we're saying here. Let the gradient be, or so f be a function whose gradient is nicely defined. Okay? Then, the conclusion, then the integral over this curve C of the gradient of f dot dr. And then it's essentially the same thing. Can be attained by, you think of the gradient as the derivative now. And so the antiderivative of the gradient is that original f. So it's your f at your endpoint RB minus your f at your starting point RA. So let's just try some examples here. So this first one will be somewhat silly. Evaluate, so the integral of the gradient of dr for f of xy equal to x squared plus 3xy plus y squared if, okay, C is parameterized by, let's just do this, x equals cosine of t, y equals sine of t, and t goes between 0 and pi. And then B, C is parameterized by x equals negative t plus 1, y equals 0. Okay. And t goes from 0 to t. All right, so we're going to just apply this fundamental theorem and you can leave it up like this. Right? And so, right, our R is cosine sine, right? Whatever that X and the Y gives you your R. And since we're integrating the gradient, right, we can just apply this from, I don't even need to figure out what the gradient is. We could if we want, but let's not on this one. And so for A, right, we're just going to apply our theorem. F dr over C is just your function at your endpoint. So in this case, with the first parameterization, our endpoint is R of pi, right? R of pi, and then minus F R of 0. Okay, and so let's just plug these in. So what's R of pi? So cosine of pi is -1, sine of pi is 0, so it's -1, 0, right, as a vector, but you know, it means we just plug it in as your x and y. And then for 0, what do we get? 1, 0. And then we have our function right there. And so what do we end up with? X squared plus 3xy plus y squared. So if the y's are 0, they're gone, right? And so we just plug in, I'll just write it up. -1 squared minus 1 squared, so we end up with 0, right? Okay, how about B? So the integral C of that gradient f dot dr, again it's f of r of 2, right? Minus f of r of 0. So what's r of 2? -1, right? -1, 0. And then what's f, or what's r of 0? 1, 0, right? So, exact same thing. You get 0 as well, right? And so notice, I should have picked one that wasn't 0, but because 0 makes you think something else is going on. But the point that I was trying to make here is your curves, what's this first one? Let's just, so C being that top one. So we know it starts at 1, 0, and it ends at -1, 0. What's x equals cosine, y equals sine? What's that parameterization? What curve does that look like?
Square equals to the sum of each square.
Well, I guess, so, here, let me write it this way. So R of t being this parameterization, this cosine of t, sine of t. What kind of curve is that? Circle, right? The top half of that circle, right, is x squared plus y squared is 1. And then it starts here and it ends here, and you can check that it gives you this, right? So this curve corresponds to that. What's the second one that x equals t, -t plus 1, and y equals 0? What's that curve look like? Y is 0, so you're just staying with y equals 0. When t is, so let me write it out.
From -1 to 1.
Okay.
Yes, from -1.
Well, from 1 to -1, right? It goes backwards because of the negative t, right? You start at the, when you plug in 0, you start at 1, 0. And then as t grows, this becomes more and more negative. So you're going this way. That make sense? So this parameterization corresponds to that. And so notice, these are completely different parameterizations, right? They're not even, they're completely different curves, I should say. But they start at one point and they end at the same point, right? And notice that your fundamental theorem only cares about the point you started at, and the point you finished at, right? In both cases. So no matter what curve I pick, I could take one that went like this, right? Come up with that parameterization of that, I'd get the exact same answer, right? I'd get 0 because I just get my starting point minus my end point. Does that make sense? And so that's why, you know, knowing that a vector is conservative is so important, because it's really easy to compute a vector field is conservative. It's really easy to compute these integrals using this idea. Does that make sense? Okay. So let's just do a couple things. I already basically mentioned this, but let's just do it. Recall, f is conservative if, so what was the definition again of being conservative?
Gradients of f is equals to capital F.
Right,
That's
so,
it.
so capital F is the gradient of some little f, right? If this is true for some little f, right? And so the fundamental theorem for line integrals essentially says that for, I'll just write it out. The fundamental theorem for line integrals, we'll abbreviate it with this really nice FTLI from now on. Okay, just says that if f is conservative, if f is conservative with potential function little f, remember that's what the little f means, right? It's the function whose gradient is that. And C is a curve from P to Q. I'm going to leave off some details. The curve has to go through, you got to remain in the domain of your f, right? So it does, if your function isn't defined and you leave that domain, of course you're not going to have an integral. And so I say this curve is defined from P to Q. I'm assuming that curve stays in the domain of this function. But if all of that is true, then your integral, your line integral is just your potential function at your finishing point minus the potential function at your start point, right? And so if you can show a function or a vector field is conservative, then we'll be able to easily integrate these things without even worrying about what the parameter is. So let's do an example here. So first part, show show that this vector field is conservative. For now, let's just do it by finding a potential function, okay? So find a potential function like we did last time, and then evaluate the integral of f dot dr, where c is parameterized by sine of 2t, comma, cosine of 2t, and then t ranges between 0. So first, find a parameterization for, find a potential function for the capital F, and then once you've done that, just apply this fundamental theorem. So, let's work through this. Maybe I'll just come off to the side, because this one should be pretty easy right here. You first assume your f sub x is that, right? The 2x plus 2y, and then what's f? X squared plus 2xy plus some gy, and then your f sub y would be 2x plus g prime, and then what is it supposed to be? 2x plus 3y squared, so you know 3y squared is your g prime of y, so what's g? Y cubed, right? And so your f should be x squared plus 2xy plus y cubed, right? So there's your a. And probably in the not too distant future, we'll see enough of these that you might get comfortable where when you see this one, you can just say, okay, I know I need x squared plus 2xy, right? And I know then I need 2xy and y cubed. You might be able to just write that down right at the start and just say, notice this is the, right, is the potential function for this. But if nothing else, you can always, just take your time and work that out. Okay, so that's all there is to A, and then B should be easy, right? Now that we have a potential function. So again, and I'll use the notation from before. Let me call this guy R. Okay. So if I plug pi in, what do I get? Sine of
0.
2 pi, so 0. And then 1, right? And what about when I plug in 0?
0, 1.
0, 1, it doesn't actually matter what the potential function is, it's the same point, right? So I have 0 here. Okay. And so let's just remind ourselves, what does this curve look like? So sine squared plus cosine squared is 1, so it's a circle. And we've already seen it ends up back at the same place, but remember, right, it's going faster because of the 2, it just goes around the circle quicker. And so you come around like this. And so if you had noticed that, you probably wouldn't have had to do any more of the problem, right? If you say a conservative vector field, well, I know I can evaluate it by doing f of starting point minus end point. Well, if they're, right, if the starting point and the end point are the same, you're always going to get 0, right? Anytime you're on a closed loop, okay? And so we have a couple sort of related ideas here. So a closed curve is simply a curve whose start point and end point are the same, right? And so you might have, you don't have to draw this. That's a closed curve, right? I came back to the same point. Be careful though, because, as you're doing parameterizations, if you start to trace back over something, is it a closed curve? I mean, I would still say yes, this is, because it's the curve you're interested in, not exactly where you are on there. When you talk about something like this. So for instance, I don't know that I would ever ask this, but on this problem here, right, if instead of going from 0 to pi, I went from 0 to 2 pi, that's twice around the integral, or around the circle. If you're just asking about the line integral on that curve, well, that really, there's two different ways to think about it, but you should, so I should be careful here. I think I'm going to leave it. You should be careful about whether they really just want the line itself, or if you really want to do the path twice, right? There's two different answers you'd get for a lot of examples. If you sort of go or ring around something twice, you might add everything up twice, right? Whereas that might not be what you want. Maybe you really are interested in just this. Because when you say the line integral over C, if you're just talking about the curve's just the circle, right? Not twice around the circle. And so you got to be careful about what's being asked for. I don't know that that's going to come up very often, but anyway, be careful. Oh, and then So a curve, a closed curve is one that just ends where it starts. A vector field is path independent, right? If every, so, let me finish. I don't want to write down the full definition. So F is path independent if, let's write it this way. If F dot dr over C1 will be the same as F dot dr over C2 if C2, if C1 and C2 have the same start and end points. Does that make sense? So being path independent means that if you start at some point here, P, and you take C1 and you end up at B, and you take C2 and you go, you end up at Q. So a vector field is said to be path independent if this is always true. It doesn't matter what path you take to get there. Okay. And so let me just point out, so if your path independent, and so I guess we haven't talked about this yet. So if we have a path C, what do you think negative C means?
The opposite direction.
Just go backwards, right? So just go backwards. So whatever your starting point was, you finish at the other point, right? And so this isn't a full proof of anything, but let me just say this. So path independent means that the integral over C1 of your F dot dr would be, so again, keep in mind, I'll draw this picture back up here. So you're going from some P to some Q along, I'll draw it this way, along C1, and then you might also go along some C2, right? And so if these two are equal, right? That's what it means to be path independent. Then it should be true that that's if and only if the path along C1 of F dr minus the path along C2 of F dot dr is 0. Okay? But then I guess we should be a little bit careful here. So what's dr?
The vector.
It's the parameterization, and so dr is the derivative of r times t, right? Or times dt. And so if you are moving in this direction, your derivative is going to be pointing in this direction, right? If you turn around and you move backwards, your derivative is going to be pointing backwards. Does that make sense? So when you take the derivatives along this curve this way, along C, your derivative, your r prime points that way, but if you're moving backwards, it's going to point that way. Does that make sense? So your dr will flip signs depending on which direction you're going along your parameterization. So I didn't bother talking about that before. Maybe I should have. When we had integrals, line integrals before, and we had the line integral of some function of x, y, x and y ds, that's always going to be the same thing as the line integral over negative c ds. Because what was ds? It was the change in arc length, right? And so that doesn't have a direction to it, it's just a number, it's a positive number always. And so it doesn't matter which path you went, or which direction you went on your path, you get the same value. Remember, we talked about how this formula should correspond with some curve, and then maybe, right, the area of the thing sitting above it, right? And so it shouldn't matter if you went this way or this way along that path, you should get the same value. Whereas when you're talking about moving through a vector field, right, the work done in one direction, you might be being opposed by the vector field, in the other direction it might be helping you, and so the work is going to change dramatically. Anyways, my point is, this becomes this plus the integral over negative C2, right? So for dr, you get that. And then what's negative C2 look like? So this is a completely different picture here. But here's C1, and then negative C2 will just go back the other direction, right? And so that'll be a closed loop. You'll start here, you'll come back to there. And so if you call this whole thing C, right, this is the, that's my if and only ifs, the integral of C of f dot dr equals 1. Okay? And so this is our next theorem, essentially, right? If you have a loop and the vector field was path independent, you can just sort of split your loop up. Well, I shouldn't even say that. Path independent, you really could just start at 0 and end at 0. If you know that every loop gives you 0, then you can prove your path independent. So if every closed curve gives you 0, then you just work your way back up to end up with path independence. Does that make sense?
So is that this term for C is equals to C minus C2?
Yeah, it's, well, C1, yeah, plus the negative C2. So here's really the way we're going to work it, right? So the theorem that we want is that this being true means you're path independent. So if every closed loop, every closed curve gives you 0, then you're path independent, right? Because the idea is if you know every closed path gives you 0, then you just, and you have two different paths, you just make the closed path by doing this. You know that 0, which means this is true, which means this is true, which means this is true. Does that make sense? And so that's the theorem. Essentially, that's the proof of it. But I was being a little bit lazy in my proof. Hopefully that makes sense. But let's just say this. So, theorem. F is path independent on a set if and only if the integral over C of f dot dr was 0 for every closed path. C and D. Okay. All right. So we'll use this a little bit. All right. So let me just say, so what we've seen, all right, so this is an if and only if statement. We saw this was true for conservative vector fields, right? Because you just take f of your start point minus f of your end point on it, and really it was true even before that. So we have shown, that conservative vector fields are path independent. Okay, and so the question is, what about the other way around? If you know something's path independent, can you guarantee that it's a conservative vector field? And the theorem is basically yes, or the statement is basically yes. But there's a couple little things we have to put in here. And so let me state the theorem here. And I'm going to be pretty vague about a couple definitions. I'll draw pictures over here. Talk about what we're looking at. But let me just state the theorem first. So let F be a continuous vector field. So here's where I'm being a little bit vague. On an open, connected set D for which so sometimes I kept saying the vector field was independent. I can't remember what your book's terminology is. Sometimes people will only talk about the line integral being path independent. So independent. Path. Then F is conservative. Okay, so there's the converse, right? That being independent of path implies you're conservative. And so the only tiny caveat in there is it's assuming you're on an open and connected set. And again, I don't want to get into the details of what it means to be connected or open, but let me just draw a picture. So what is an open interval? Like an interval from 1 to 2 is an open interval if you put those on the ends, right? Parentheses, and then it was closed if you did this, right? And so what did open mean? It just means you don't include 1, right? And you do include 1 means closed. And so if you think of something in 3 dimensions, right? Open just means you don't include the edge, right? And closed means you do include the edge. Does that make sense? So that's all that means. If you can go out to infinity in directions, that's considered both open and closed in some sense. But essentially, for our purposes, we can think of it as open, right? If you can go out everywhere or far in one direction, that's open. Okay, and then connected just means. So this is connected. If it were talking about this region plus this region, that's not connected, right? You can't get from here to here staying inside your region. Does that make sense? Now, even something weird like this, make sure you draw that exactly like I did, is connected because I can get from here to here, not by my straight line, but I can follow a path that gets there, right, and stay in my region. And so that's the idea. And so there'll be ideas of simply connected later on that we won't worry about right now. But let's just use this theorem. Okay. All right. Let's see. All right. Let's do this first. I want to prove something. Well, let's prove this theorem first. Can't decide on the order of this. So if a vector field F, we'll put it in 3 dimensions here. Let's do P, Q, R. Is conservative. Then the curl of F is equal to 0. Okay, so this is one direction. It doesn't, the important direction is going to be the other way. If the curl is 0, then it's conservative. That's the way we're going to want to use this. But for right now, let's just prove the first direction. And so we'll actually prove this one. Okay, so suppose F is this vector field PQR is conservative. Okay, so this is mostly just practice talking about partial derivatives and curl and some other stuff. So then, I'll just write it this way, then f is, so in particular, the p, the q, and the r are what? They're little f sub x, right, little f sub y, and little f sub z. That's what it means to be the gradient, right? And so now let's just compute the curl of this, right? So the curl of this gradient. And so you might have already, I think I didn't prove the curl of the gradient to 0. Maybe I should have back down, but let's just do that. So then the curl of this f. So remember, curl was what? The del operator dotted with your function, or crossed with your function, right? And so what's that look like? So I'll just do a reminder. So it's this operator, right? Partial with respect to x, with respect to y, with respect to z. And then we plug in our function f sub x, f sub y, f sub z. And so compute the curl of that, thinking about notation. Remember, what's this mean? F sub xy means
F sub.
do f sub x and then y afterwards, right? So pay attention to that. I mean, all these are going to turn out to be 0, but I want you to write them in the correct order. So try to compute that curl for 2 seconds here. Okay, so when you do the first part, what do you get? The derivative this way, so what's that?
Fy minus f.
F,
Y, Z?
no, it was already z, right?
Oh,
And then you take it with respect to y, so that's
Z first.
fzy. And then this way will be minus fyz. Now, we know that it doesn't matter, right, which order you do it in, but I just wanted to make sure that's really that. And then the other ones will be what? The middle term,
Z,
I'll just write it this way, negative z then x, right? Minus x then z, comma, and then zy, oh, right, yx, right? Yx minus xy. Okay? And now we have that theorem, right? Again, under some conditions, which almost every function you're going to encounter satisfies, these are all 0, right? So you get 0, 0, 0 for pretty much every function you're going to. What was the, what did curl measure? You remember? It was measuring where did curl point? Curl's a vector, right? You got a vector field, and it points, if you had a rotation, right, it points out of that rotation. But the point is, it's measuring how much your function is sort of curving around in a specific direction, right? And so, if your curl of your vector field is not 0, right, you should anticipate. So that just means that it's not just wrapping around like this, right? It's not spinning around in this little vortex. And so you should anticipate that you should be able to get a little, maybe a little tiny circle, but someplace where you're not just wrapping around this thing, right? And so essentially, right, if you're not curling around, you zoom way in, it should behave like this, right? And so hopefully you can guess that on this kind of interval, right, this guy won't be 0, right? Because your vector field is pushing in one direction through there, and so as you wrap around, you can do this. So if your curl's non-zero, you should be able to find a little tiny closed interval where your closed path where your line integral isn't zero. Okay, so we're going to come back to this next time. I don't think I have time to do it in 10 minutes. So, yeah, I don't think I want to do it in 10. So, we'll come back to this next time, but essentially what we're going to show is that if you have so a non-zero curl means you're not path independent, right? It means you're not conservative, okay? And so we're going to basically show that curl is a measure of whether or not you're conservative. Before we finish today, though, let's do a couple of simple examples, and then we'll come back to the sort of broader question next time. Let's see. I think we kind of did this last time. Let's just do this. Show the following are not conservative. Okay. So, I guess I just erased it. What was the theorem that we had shown a little while ago, that if you were conservative, then the curl was
Zero.
zero, right? We haven't shown the other direction yet. We haven't shown that curl being zero means you're conservative, but we can at least say if your curl isn't zero, you are not conservative. Does that make sense? And so to show something's not conservative, it's enough, well, it will be enough, but for now, let's just look at its curl. So again, just practice curl here. Take the curl of that and see what you get.
-1, -2, 4.
Okay, so let's see. So it'll be with respect to y, -1 minus
2. No, -1.
-1, right? So it should be -2, I think, right? Is that what you guys got?
Yes.
-1 minus 1.
Yes.
And then in the middle, you should get, it'll be negative. Oh, here, so again, don't just try to write out the answer like I'm doing. You should show some work, right? Even this is good enough. But so that middle term will be what? X, which would be 0, and then B will be 0. So that whole term is going to be 0, right? And then your last term will be 0 minus X. Is that okay? And really, once you got that -2, you were done, right? Once you know the vector is not 0. This is not the 0 vector, and so F is not conservative. Okay. And I don't think we're even going to bother proving too much of the other direction. But essentially, if it is 0, it will be conservative for most examples. Let's talk about a function. So suppose your F looked like this. PQ. What's the curl of this guy?
Q sub y. Q sub x.
Well, PQ, you gotta, well, I'm sorry, should write it this way. You have to first view it as PQ0, right? You throw in that extra term, and then what did you say we got? We get 0, 0, right? And then, I think we did this before, right? Q sub x minus P sub y, right? And so the curl of a two-dimensional vector being 0 is equivalent to these guys, this equaling 0. Does that make sense? So So maybe I'll write it this way. If f is, and you really saw this theorem back in Calc 2 when you first introduced this. So I'll call it a theorem. So let this be true. And we'll state the full version next time, but let's just state it this way for now. If Q of x is not P of y, then f is not conservative. Okay, and again, it'll be the exact same thing. It is conservative if and only if that's true, but we'll wait till next time to say that definitively. So let's do one more example here. Show this, so same direction, show this guy's not conservative. And so I'll just do a little two-dimensional one here. Okay. All right, so you could just throw a 0 on the end and take the curl of it, right? That's fine if you want to resort to that. But we're just going to say that's P, that's Q. What's Q sub x? What's P sub y?
Negative 1.
All right,
Oh.
so Q sub x is negative y, P sub y, negative x, Q sub x, not P sub y. So F is not conservative. Okay? So next time we'll just basically say that the other direction is true. Maybe we'll do a little bit more detail than that. Yeah, I don't think we'll prove it. So, but essentially, we'll show the other direction, and then we'll calculate some more line integrals using that. Let's see, what do we get to now? So that's conservative vector fields. Oh, so then we'll get to Green's theorem, which is a interesting theorem that will take sort of a line integral and turn it into a double integral. And then we'll move into three-dimensional stuff and sort of do analogs and all this stuff we did for line integrals there. But let's stop there for today.